Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we are going to discuss about a simple software solution to the critical section problem which is known as Peterson solution. This Peterson solution, how it can be included into two processes, say PI and PJ, and how they are rectified this bounded weight, mutual exclusion and progress requirements, and how they can be implemented in the Peterson solution's critical section problem by reliably and smoothly. And if there is any disadvantage of using this Peterson solution, we will discuss that also. Peterson solution, as we say, that it is a simple software-based solution to the critical section problem. But now a modern-day computer system uses the low-level machine-level instructions like load and store, so it cannot guarantee a Peterson solution will provide an accurate solve to the critical section problem. However, we use this solution because it provides an excellent arithmetic description of the critical section problem algorithm to enroll a protocol that can be used to solve this critical section. It also illustrates some complexities that involved in designing the requirements, that is mutual exclusion, progress and bounded weight of this critical section problem. Now in Peterson solution, we can restrict only two processes that execute and swap between their operation of critical section and the remainder section. We name these processes, for example, P0 or P1, or say Pi or Pj, where j equals to 1 minus I. Now these two processes in the Peterson solutions can share two data. Now we will see that what are they. These are the data that needed to be shared in the Peterson solution. The first turn is the turn, which is an integer variable. This turn variable is used to indicate that which process is allowed to enter its critical section at a time. Suppose that if turn equals to I, then Pi is allowed to enter its critical section at that time, and process Pj has to wait along after Pi has exits from the critical section. Now the Boolean variable array flag is used to indicate that which process can ready to enter the critical section. Suppose if flag j equals to true, then process Pj can ready and can enter the critical section. So now we will see a data structure that is implementing the Peterson solution in the C or C++ program. To enter the critical section, the process Pi must first set that the flag I equals to true. By setting the flag I equals to true, as we have mentioned earlier, it is approximately telling the operating system that it is ready to enter the critical section. Suppose that flag j is also equals to true and with the flag I, then both the processes are ready to enter the critical section. Now the variable turn will determine that which process is allowed to enter the critical section. If both the processes roughly can say that allowed to turn to the critical section, then the value of turn is I and j simultaneously. But then both will enter the system, but one will last and other will only enter and immediately overwritten by the other system. In this way, turn can be given to only one process at a time by allowing it to enter the critical section. So we will see that what happens next. By writing turn equals to j, it is allowing that Pi is telling that if any other process, say process j, can wish to enter the critical section, then it can do so. Now, to allow the Pj to actually enter the critical section, two conditions must be satisfied. So we can say that this is the entry section of our program. Now the critical section will be executed by the process J. So we now prove that this solution is correct. So to prove that, we must satisfy the three following conditions: that mutual exclusion is preserved, the progress requirement is met, and the bounded requirement is satisfied. So to prove the first requirement, that is a mutual exclusion, we can set these followings. Now we know that Pi can only enter the critical section if either flag j equals to false or turn equals to I. Now in between these two complements with the observations that flag j equals to true, we can say that P0 and P1 or Pi and Pj can both enter the critical section. But it cannot happen because Pi and Pj cannot execute successfully the while statement block simultaneously. While Pj is entering the critical section, can successfully implement this while block when Pi has to want another statement, that is turn equals to j, to successfully execute its while statement block. Thus, the both processes cannot execute the while statement block successfully simultaneously. However, at the time flag j equals to true and turn equals to j, then Pj will resume its operation in critical section, where Pi has to wait until and unless Pj exits the critical section. So mutual exclusion is preserved. Now to prove 2 and 3, we may notice that Pi can be only prevented from entering the critical section if it is get stuck in a while loop with the conditions flag I equals to false and turn equals to I. So with these conditions, they can be entered the Pi section to mention it in the critical. Now if Pj is not ready to enter the critical section, then it will set flag j equals to false, thus allowing Pi to enter the critical section by telling the operating system that it is not ready to enter the critical section. Suppose this flag j equals to true, then turn I equals to turn I or turn j equals to turn j. Now if turn equals to I, then Pi can enter the critical section. If turn equals to j, then Pj can enter the critical section. Now suppose if flag j equals to true and turn equals to j for this instance, so Pj will execute in its critical section, and after executing the critical section, Pj will exit the critical section by setting the flag j equals to false. So this is the exit section followed by the critical section. Now the remainder of the code is the remainder section. Now while we are setting flag j equals to false, thus allowing Pi to enter the system to critical section. Now if flag j equals to true, then it must also set that turn equals to I to actually let the Pi enter the critical section. As Pi does not change the variable's value of turn during the execution of the while statement, then Pi will resume its operation in the critical section, which is the requirement met of progress. And when it is not changing the variable value, then after utmost entry of Pj, Pi will enter the critical section, which met is the requirement of bounded waiting. So in this way, 3 of the requirements are solved during this Peterson solution, which can be used to address the critical section problem. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.